Well, that's great. That's fantastic. Because now I have to apologize because I can't talk genetics with you guys anymore because apparently I don't know squat. So we're gonna let it go for now. I like that we did this. This makes me happy because that really isn't genetics. That's just probability. But it doesn't apply as simply as we thought to hair color. So we're gonna let that go and talk about gambling instead. So I'll stick with my field of expertise. Stop pretending that I understand biology. So
you should erase the O's and H's there. That's might confuse somebody.
That's okay. That was just me trying to work out that link you had found. Okay, so friends, let's bridge the gap between now and Wednesday because that was the question of what we're going to do on Wednesday. So we can kind of do two things at once here. Two things at once. You got your dice. We're going to leave coins behind. No, before I leave coins completely behind, realize that you can simulate with your TI the chance of any outcomes for any number of coins, couldn't you? So if you wanted to flip 3 coins, just go random 1, 2, 3. Does that make sense?
Yeah.
So if I was to do that, here I am lying to you, go back to coins now. 1, 2, 3. There. I just flipped heads, tails. I just went tails, heads. I just went heads, tails. Your neighbor would think the coin was rigged because you got the same thing you got 2 back. And he would think, you can't get that again. You have to get something new, right? This is, remember, Josh, you called it backwards this. Yeah. I call it just not being random. How many people, if you were to simulate throwing the coin 3 times, would get the same thing on the 3rd trial as they would on the 1st? Not very many of us, I would imagine. Not very many of us, I would imagine. I told you about Jenny Cruikshank in Tonal Fit with the 1, 2, 3 push-ups, right? I told you about that, right? Yeah. The 1, 2, 3s. She has never yet doubled up on an integer. So in other words, 1, 2, 3 push-ups. 1, 2, 3. She calls the numbers out pseudo-randomly, and then we have to go to that position. So she'll often do things like 2, 1, 2, 1, 2, 1, 3, 1, 3, 1. She never goes 1, 1. She never calls a repeat, which makes it, in my opinion, extraordinarily unrandom. Well, or that. But remember Monty with the Doors last week? Remember Monty with the Doors last week, right? Monty with the Doors. How many times did somebody have the prize behind door 2 and the next person also had the prize behind door 2? It happened quite a bit. As a matter of fact, I remember there was a run when like 5 of you had the prize behind door 2. Because that's randomness. Randomness doesn't neatly compartmentalize. Oh no, oh goodness no, goodness no. It clumps. It's in unpredictable ways. But it will clump. And that's what's kind of fun about it. And that's where craps comes in. So let's get back to this now. Let's get back to this after I write down. So, what I want to do is begin an orderly study. I just had an idea for 2 quizzes for you guys. For those of you guys that are short on quizzes, I just have an idea for 2 of them for next week. Okay. So what we're going to start learning about today is a way to organize probabilities of an experiment. So we're going to link under probability the idea of a probability distribution. Now this is a 243 term that we spend about half of the class in. But that doesn't mean it has to be just in 243. It can very easily and should be a part of your guys' class right here. I used this idea when I decided which healthcare plan my family should select when I started working at COCC. It's very, very easy if you work for a full-time job and they offer you health insurance to just grab whatever they call the Cadillac plan, right?
Right.
Which is the most expensive plan for you. And it pays the most when you go to the doctor. Like if you want to go to the doctor for a checkup, you don't pay anything. There's no copay. If you go in for surgery, you pay 10%. You're off the hook for 90% of it and things like that. And that's a very generous plan if you go to the doctor a lot, right? But if you don't go to the doctor a lot, it doesn't make as much sense. Right. Because you're spending a lot of money every month for a premium of a policy you're never actually going to use. Does that make sense?
Mm-hmm. That's how my husband and I looked at it.
Say that again.
That's how my husband and I looked at it.
Good! That's how everybody should look at health insurance.
The more
are
likely.
Yeah.
Say that again.
But you don't know when you're going to need it.
Hold that thought.
Yeah,
that's what Wednesday's all about,
yeah.
Ashley. That's what I've got planned on deck for Wednesday. I'm gonna check my own mortality according to the CDC. And we're gonna develop a life insurance plan for me. You guys are gonna be actuaries only. It's gonna be fun, I think.
Sad to make your own life.
No. It's, if you can treat it objectively, if you can treat it
That's good for
objectively,
your
it's
kids.
really interesting.
Way to word it right. Way to word it right.
She's being very objective. She's being very objective. Nothing wrong with that. Nothing wrong with that at all. Okay, so anyway, back to this. That a probability distribution is a way of indicating the probabilities across an experiment. We did an experiment last time. Let's do experiment number 1 again, and then we'll do experiment number 2. That's probably what we're going to have time for today. Experiment number 1 was rolling a single die. Roll a single die. Now we know, good, thank you. Thank you, Josh. We know when you roll a single die, what can happen. What can happen?
Well, I got one.
You got a 1. What else can happen? 2. What else can happen?
3.
What else? What else? What else?
6.
What else?
On corner?
There we go, yeah, the corners and the edges. It might hang in the air. I've thought about that actually with birds. When birds die, do birds ever die just flying along?
Oh my God.
Yeah, they do.
Do they just die and
Remember
they just...
those birds that fell out of the skies a couple years ago?
No, I don't mean like a disease bird, like a normal bird. They just got old, like they're just flying along like, well, it's been a great life. Does that happen?
They probably can't fly anymore if they're that old.
Okay, because my chickens all died. They fell off the perch. They died at night. They were just like asleep at night, and I go up in the morning, they're just laying on the ground. I'm like, oh, hi, Gertrude. I buried her. I was just curious, do birds just die? Anyway, sorry, I thought about that when you talked
You
about
should ask Rebecca.
I don't think they'd have
Rebecca.
the energy to fly.
Sands.
Yeah,
Walk Sands.
Walker Sands, yeah.
She would know that?
Oh yeah. She might know.
She
We
probably
took
would.
animal psychology with her.
Oh, animal psych. I was like,
Yeah,
she's
animal
psychologist. How did she know
psych.
that?
Yeah.
Sorry, I didn't mean to derail that train. Sorry. So, but we know the outcomes, yes?
Yeah.
So what we're gonna do, I'm gonna call this X. Just there's a reason I'm calling this X, and we'll come back to this on Wednesday as well. We're gonna call this the number seen when we roll the die. And now we make a laundry list of those numbers. 1, 2, 3, 4, 5, 6. So what you've just listed out is the sample space. You've just listed out the sample space of your experiment. This is everything that could possibly happen, 1 through 6. This is called a random variable. Don't worry about memorizing that. It's not important to memorize. We'll explore it a lot in 243. But what you've just done is, if you have the experiment of rolling a single die, this is everything that possibly can happen. Fantastic.
So X is sample space.
All these values combined are the sample space, right? All these are combined are the same. Each one of these is an event. Each one of the X values is an event, but all of them together can make up the sample space. Does that make sense, Christina? It's a great question, thank you. What do you think goes in this column right here?
How many times that event occurs?
I love that. Let's make it even simpler. Because you don't want to have to make this based on a certain number of, say rolls. So not how many times the event occurs, but how
That it occurs?
how likely or how often it occurs. So you don't want to say it's 20, because that implies you will have rolled the die 120 times. You don't want to say it's 10, because that would imply that you've rolled the die 60 times. We're going to say, how often does a 1 occur? 1/6 of the time. So what I like to call this column is the probability of X column. And that's why I call it a probability distribution. In 243, we'll separate this from frequency distributions. Don't worry about that right now. We'll go back to that in 243, I promise. Probability distribution. So what you do is you list all the probabilities as you go down. So each of these is going to be what?
1/6.
Yes.
2/12.
Yes. Good. And right, exactly. If you treat it empirically, like we did on Wednesday of last week when I had you guys rolling a die, we kept track of the occurrence of the 1s and the 2s and the 3s and the 4s. Actually, we were trying to disprove something. We were trying to see what 1/6 meant, if I remember correctly, right? And Brittany, you brought it up. You said it was the average. It's the average rate of appearance, which is another way of talking about the empirical or experimental definition of what 1/6 means. On average, you will get 1, 2, for example, out of every 6 rolls, on average. That doesn't mean that you sometimes don't get all of them come up 2s, or none of them come up 2s, but it averages to 2. That's what we spent the Wednesday on the backboard doing. That was fantastic. That was a fun diversion. I like that. Now, one of the most important things to be able to do with a probability distribution is find the average of it. So here's a question I have for you guys. On average, what do you roll? So if you roll a single die, what's the average roll that you roll?
Well, what kind of average?
What do you mean? That's a good question, actually.
Didn't you say that there was like more than one?
Sure! There's a mode, there's a median, so can you pick one?
Alright.
Which one would you like to talk about? Oh, okay. Which average should we talk about? This is good. Should we talk about the average, which is what Brittany described to us about 2 weeks ago, 3 weeks ago maybe now?
Yes.
And your average was what?
To add everything up and divide by however many you have.
Add everything up and divide by how many you've got. Okay. Now, I love that. Except this has to be a weighted average, doesn't it? Doesn't this have to be a weighted average? It has to be because they have weights.
Equal weights though.
Good. Thank you for that, Josh. We'll come back to that if you don't mind. We'll come back to that. But if you have weights, whether they're equal or not, we have to account for them. The reason, I love that you brought that up. The reason I'm saying, regardless of whether they're equal or not, is if you treat the weights, even if they're equal weights, correctly here, you'll always treat them correctly, even when they're not equal.
Gotcha.
Thank you, sir. Thank you, thank you, thank you. So, remember how we did weighted averages last week? How do we do it? How do we do it? Explain to me again.
1 times 1/6.
Excellent. And then 2 times,
And then
love it!
2 times
Yes!
1/6.
So on average, thank you, that's perfect. So we got 1 times 1/6, plus 2 times 1/6, plus 3 times 1/6, plus 4 times 1/6, plus 5 times, I'm sorry, I'm saying that very loud.
So exciting.
It is exciting! What do we have to divide by? Because Brittany told me weeks ago you have to divide by something then, right?
Don't you have to add all those up?
Yes, you have to. Now watch this. This is what's so cool about probability distributions. We have to add this column up right here and divide by the weights. What happens when you add up all those probabilities?
You get one.
You get 1. Now, that makes sense for a whole lot of reasons. Give me one reason why it makes sense when you add up all those probabilities, they add up to 100%. Please, Marichelle!
When you roll each side of the dice, it's 6, 6.
So you've accounted for everything, right? If you roll a die, either you're going to get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. 100% of the time, something up here is going to happen. You've got every possible outcome accounted for 100% of the time. I love that. That's great. So in other words, we have to divide that whole thing by 1, or we just leave it like that. One of my favorite results of probability distributions is that we can stop once we've done this times this, plus this times this, plus this times this. You're done. Add that up and that's the average. What does it add up to? That's a 1/6. That's 2/6. That's 3/6. 4, gesundheit. 21/6.
That's what I just said.
3.5. On average, you roll a 3.5.
Is that on like one?
Your neighbor's head just exploded. He's still working on the damn who's trimming the clippers this weekend. And now you tell him the average roll's a 3.5. Amy,
I just added up those and got 21 and said 21/6.
hang on.
That's
That
what I
will
do.
only work, as Josh pointed out, when the outcomes are equally likely.
Right.
Okay.
It will not work when they're not, and here's why, When I was describing how Chuckleluck works in my 243 class, the payouts are -1, 0, 1, and 9. They added those up and said, you're going to make 225 on every game. I'm like, no, you're going to lose 50 cents on every game. And they said, no, I added up -1, 0, 1, and 9. I said, yes, but you're assuming those are all equally likely. Oh. So that's the thing. I'm trying to always account for those. We'll get to one in 5 minutes where they're definitely not equally likely again. We'll promise. And then soon with craps it gets even better. What does it mean to average 3.5? Can you roll 3.5 on a die?
No.
No. So what does it mean to average 3.5?
Yeah, it means it could be like either a 3 or a 4 on average.
Okay. Remember in the 1990 census in America? Maybe you don't. There were 2.5 kids per family. What the hell does that mean?
Means they cut their kids in half and
That's one way of doing it. It's one way of King Solomon. One way of viewing it, right? Please, Autumn.
For every 2 kids.
In one family.
In one family, there was 3 kids in another.
There was 3 kids in another family. Thank you, sister. Very nice, very nice. For every 4 kids in one, there was 1 in another.
I always thought it was because they had one on the way.
Well, I mean, technically speaking, they wouldn't have counted that one yet in the census. So what does a 3.5 roll mean? For every time you rolled a 1, somewhere else you rolled a 6. 7 divided by 2 is 3.5, right? Every time, yeah, I know, it's thrilling. Every time you rolled a 2, somewhere else you rolled a 5. For every time you rolled a 3, as Josh has pointed out, you also roll a 4 with equal likeliness. Likelihood, I should say, not likeliness, I'm making up a word. Is that fair? So yeah, you can't roll 3.5. But if you spread the dots out, and here's where it gets interesting, right? If you take the time you saw 6 dots and the time you saw 1 dots and you spread those dots out and share them, every face has 3.5. Remember the sharing idea, the idea of the communal spread of the data values? That's what's going on. You can't actually roll 3.5, but that's what the average roll is. Yes, Josh?
Does this have anything to, is this related to the fact that 6 is across from 1 on the die and
I don't, you know, I've thought about that. Every die is made that way, but that has nothing to do with the way they fall.
Yeah.
But it does have something to do with the way they used to be cooked. Remember we talked about cooked dice in here? I think I told you about this, right? Put them in the oven. If you want to, for example, roll 7 more than anything else, you put 7 facing up you put your dice facing up, 7, in your oven. And put them on, I don't know the science behind this, but there's a certain temperature that will slightly melt them. And what that does is, it melts them, gravity pulls the molten down, and the bottoms get heavier, which means slightly more weight on those sides, which means they're going to roll 7 more, because the heavy sides opposite are going to go down more. Now, that has nothing to do with the likelihood of 1 versus 2 versus 3 on a fair die. I don't know why they do that on the dice. It's just the way they always have been done. It's the same reason, why do we have 4 suits in a deck of cards, and why are they hearts, diamonds, clubs, and spades? I have no idea. I'm sure there's a historical reason, I just don't know what it is.
They're named after, like, kings or something?
You see, there is a reason, I didn't know that.
And,
Yes.
like, what's his face?
Oh, Charlemagne and...
Yeah.
Right. Jesus Jones.
Yeah, yeah.
Jesus Jones?
I'm making things up. 90s pop star. I'm making things up here. Sure, it's all historical, and I'm sure the dice are too.
Yeah.
And the chessboard, I'm sure, is also historical in many, many ways. Cool, thank you. Now, let's take our first move towards craps. Because that's what I'm interested in, and you should be too, because that's what I want to head to. So we'll make our first move towards craps. I want to come back, Ashley, to what we were talking about before with the life insurance policies. We'll do that on Wednesday. And then we'll come back to craps next week. But all of it's going to be tied to this idea. It's all tied. Because when you talk about a life insurance policy, essentially what you're doing is making this for the amount of money that you're either paying in or taking out of the policy. And that'll make more sense on Wednesday once we do some stuff. And I'm going to do some Googling between now and then. Let's go back to this backboard. You guys are all on camera. That's wonderful. There is. I use it frequently. Well, I shouldn't say frequently. I use it occasionally.